Okay, theorem 9916. So we need to today prove this. We have already seen the statement, but before we start the proof, let us once more briefly see what it is saying. So here the claim is that any function of this type that is continuous is also necessarily uniformly continuous as well. The focus here is the domain. The domain needs to be a closed bounded interval. The proof is by contradiction, so we will suppose that f is not uniformly continuous and then we will try to get some kind of contradiction. So let's start the proof. Suppose f is not uniformly continuous on the closed interval a comma b. Now you recall that we have already seen one result in this section. Although we haven't proved it, we will do the other proofs in the exercises. That result says that a necessary and sufficient condition for a function to be uniformly continuous is that it maps a pair of equivalent sequences again to a pair of equivalent sequences. That means the supposition that we now have about f means that we are going to get a pair of equivalent sequences that f will map into a pair of non-equivalent sequences, and those sequences we will get here from this set, and that result is proposition 998. So because of this supposition, by proposition 998, there exist sequences, say we call them xn and yn, in the interval a comma b that are equivalent, but these sequences obtained by applying the function f to the terms of the original sequence, this and this, are not equivalent. Let us now focus on these two sequences being not equivalent. Being equivalent means what? It means that the sequences, when we say that two sequences are equivalent, it means that they are eventually epsilon close for any positive real number epsilon. So that means these two are not equivalent. That is going to mean that there exists at least one epsilon for which these two are not eventually epsilon close. Now that also we need to understand carefully. Thus, there exists a positive real number epsilon such that and are not eventually epsilon close. We understand why this is the case, but now it has a consequence. So the following set is infinite. E. What is E? E is the set of those natural numbers n for which the numerical difference between f of xn and f of y, I don't have space here, let me write from here, is strictly greater than epsilon. Okay, now fxn and fyn not being eventually epsilon close means that this set is infinite. Why? But how exactly is it implying that this set has to be infinite? If this set is finite, let us see what happens. Suppose E is finite. It then means that there are only finitely many natural numbers n, finitely many suffix values for which this difference is greater than epsilon. So if this set is finite, then there exists a largest element in this set for which also this inequality will be true. But what happens if you take even larger integers, larger natural numbers? Then for all of them, the opposite inequality has to be true. That means if we were supposing that E is finite, let me just actually write the steps here. If E is finite, then it has a largest element we should never take anything for granted. We should see every step carefully and understand precisely why something is true. The moment we take something for granted, it usually is the case that there is a gap in our understanding and we end up learning something wrong. Okay. So if E is finite, then there is a largest element. Let me just call it M in E, which means that m plus 1, m plus 2, all these natural numbers will be outside E. And what would that mean? That would mean that this would be less than or equal to epsilon for all natural numbers n greater than or equal to m plus 1. That's because all of these values of n are such that they cannot lie in E. That is why. And why is that so? That's because m is the largest element in E, so larger natural numbers, none of them belongs to E. And that is why for none of them this inequality is true. That means the opposite inequality is true. But then what are we getting? Then we are precisely getting the fact that fxn and fyn are eventually epsilon close, and they start being epsilon close term wise from this stage. But that is not the case, and that is why E cannot be finite. But then fxn and Fyn are eventually epsilon close. This is the reason for E to be infinite. Now note that E is an infinite set, but E is also a subset of the set of natural numbers. Now we recall a result that we saw when we were studying the system of natural numbers, infinite sets, finite sets. So there we came across a result, proposition 815, which says that when you have an infinite subset of n, that needs to be countable. Now, by proposition 815. Proposition 815 means it's from the 8th chapter, which deals with infinite sets. E is countable. Let us also recall that by countable we mean countably infinite. Some people call such sets countably infinite. E is countable. In fact, the proof of this proposition shows that there exists a sequence, say Nj, in E. That means all the Nj's are elements in E. Maybe not all the elements in E, but elements in E, some of them in E that is strictly increasing. Let me continue from here, which means that n0 is less than n1, n1 is less than n2, and so on. Alright, so we have got a sequence of natural numbers that is strictly increasing. Now what? Now we are going to, well, for this sequence, since all the Nj's are coming from E, clearly for every term of this sequence, we have the kind of inequality that is there in the definition of E, that is f of x nj minus f of y nj is greater than epsilon for all natural number j. This is because all the nj's are elements in E, that's why. Alright. Now we are going to consider the subsequent. Remember, we have the original sequences xn and yn. Now for these specific values of n, that is nj, we can consider the subsequence xnj. Since the subsequence xnj is in this. Did you see why this is a subsequence of xn? simply having nj here is not enough, but these suffix values need to themselves form a subsequence of the sequence of natural numbers that they are doing in this case. In other words, we need to have this strictly increasing nature in the suffixes in order for it to be a subsequence of the original sequence xn that we are having here. Okay, so there is no problem calling it a subsequence of xn. We don't write that, we understand. Now the point here is that this is a sequence in a comma b which is compact, so we can use Hein-Borel theorem. It follows from the Hein-Borel theorem that this subsequence in fact itself has its own subsequence that is convergent inside this set, that there exists a convergent subsequence, because we already have suffix of suffix, now we have another suffix of even that. So we need to write these things somewhat carefully. We don't usually have this extent or this level of suffixing, but here we are forced to consider such a situation. It's a little inconvenient, but soon it will go. Okay, the proof will be over. So what are we having here? Theorem that there exists a subsequence of even this. X n j k, so where now k will vary, and actually jk and hence extend jk, everything will vary, but the index here is k, that converges to some L, again here in the same set. That's what Hein-Borel theorem states. That is, limit of x n j k as k approaches infinity is equal to L, and that L is a number in the closed interval a comma b. Now recall that the original sequences xn and yn are equivalent, and we know from a previous result that when we have two equivalent sequences, their difference is a sequence that converges to 0. Do we mention that here, or we just simply write? I mean, it is something which we saw in the beginning of this section itself. That is a necessary and sufficient condition for two sequences to be equivalent, that their difference converges to 0. So we simply write, since xn and yn are, we need to close this, okay, infinity is always closed, are equivalent, so limit of xn minus yn is equal to 0. Now what can we say about xnjk from this situation? Note that xnjk after all is what? The original sequence is xn. When you considered xnj, that was a subsequence of the original sequence. But then when you considered xnjk, that is the subsequence of the subsequence, which ultimately is a subsequence of the original sequence only. And that is why if we use these suffix values only, n, j, k, then actually we are just looking at a subsequence of xn. Just like that, xn jk minus yn jk is a term which in the subsequence, corresponding subsequence of xn minus yn. Since xn minus yn converges to 0, so by a previous result from the section on subsequences, xn jk minus yn jk also converges to 0 because it's a subsequence. Thus, limit of xn jk minus yn jk, here however you need to write k tends to infinity is equal to 0 because this is the index of this sequence, which is a subsequence. Now you look at these two limits, this one and this one. When you take the difference of this sequence and this sequence, say you consider this minus this, what do you get? You get yn jk, and accordingly you also get the limit L minus 0, which ultimately is simply L. In other words, by algebra of limits we then have, we can write that here. So by algebra of limits, the limit of yn jk as k tends to infinity is also equal to L. Okay. Now we use the fact that our original function f is continuous and both these sequences xn jk and yn jk are sequences in the closed interval a comma b, which is the domain of that continuous function f. And there is one more thing, this L also is a point in the domain. Why are the sequences xn jk and yn jk sequences in a comma b? That's because the original sequences of which these are parts themselves are sequences in this closed interval. That's why. Since f is continuous at L, it's continuous at every point here, in particular it's continuous at L also, and these are sequences both of which converge to L. So their f images will converge to f of L by the sequential formulation of continuity. That's why we are saying, since this is continuous at L, we are going to have these two limits. F of xn jk is equal to f of L and limit of f of yn jk is also equal to f of L. Hence, again by algebra of limits, no need to write again and again, the use is clear. I mean, it makes it clear what we are using. Hence, by the algebra of limits, limit of xn jk, well, not simply xn jk, but f of xn jk minus f of Ynjk. We are not taking modulus or anything. Okay, this is simply we are subtracting the two sequences and concluding from the algebra of limits that this is equal to, what will it be? F of L minus f of L, that is 0. This is equal to this. But now we have almost everything to draw our conclusion, which will be a problematic statement. You see, this sequence is converging to 0. Okay, which means what? So for that particular epsilon, I mean epsilon is something we have chosen from our supposition that the f is not uniformly continuous, right? And as a result, these f of xn and f of yn are not equivalent. From there we are getting epsilon. So epsilon for us now is not a variable, it's not any epsilon, but it's something specific, some specific epsilon. For that epsilon, there exists some natural number n such that, and this n we are getting because of this limit being 0. F of xn jk, we have taken it n. We can write n, but for some reason I would like to write k. F of yn jk is less than or equal to that epsilon for all k greater than or equal to k. But we already have something about this type of difference, no? However, we already have this xn jk minus yn jk greater than epsilon, not for any kind of special k, for all k actually. These inequalities are directly contradicting these inequalities. So this is a contradiction. And this contradiction stems from our original supposition, because you see, that must be the wrong thing that we did. Everything else that we did was logical. Okay, so the beginning must be wrong. Hence, our initial supposition must be wrong. What was our supposition? Namely, that f is not uniformly continuous. So f must be uniformly continuous. So that's how we have this very nice result, that if we restrict the domain of f to be a closed interval, closed bounded interval, then continuity implies the much stronger uniform continuity. Hence f is uniformly continuous. that I am not writing. Okay, that's understood. So this actually completes this section. After this, we of course have the exercises which we will do in the community section. We will solve them. And that's just it for tonight. See you in the next upload. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.